Hello. Hello.
Hello.
Hello, Colin. All right. Thank
Good
you.
morning.
And good morning, Brandon. Thank you. Thank you. Totally helpful. More than even you know. And good morning, Nasrin. And good morning, Xavier. And good morning, Gaia. Good morning. Sorry. Good morning, Emily. Good morning, Alexis. Good morning, Charlene. Good morning, Gaia. Good morning, Charlene with the double. Good morning, Emily. Good morning, direct chat people. Good morning, Michaela. Good morning, Carolina. Good morning, Alexis with the double. Good morning, Brittany. Good morning, Nasreen with the double. Good morning, Adenelsi. Morning, Ryan. Awesome. Okay. And Anissa, good morning. Okay. Okay. Let's I think we can just get rolling. I think we should just get rolling. Let's in fact, well, I'm sort of I want I think I'm going to shift right now straight to homework 6, the one that we extended. Um but I'm going to start talking about it right now. Hopefully that will help. That will help, hopefully. So in other words, you're still working on this homework, or maybe it's homework, whatever it is, the space relations homework. I will start talking about it right now. Um, and if you can use anything that I say in order to do yours, all the better. I think that's yes. But also while I'm pulling it up, obviously as I'm pulling it up, as I'm pulling up, yeah, homework 7. I'm sorry, homework 7, space relations and vectors. I'm going to start talking about aspects of it. But while I'm pulling it up and recalibrating, feel free to ask any questions about yesterday, about Monday. Um, feel free to put them in the chat and I'll answer them first before we do this. But let me just but homework 7 is my goal for right now. Yes. Okay. Okay. Um, bear with me for a second. I'm sorry. It is 7. Okay. Okay, thank you, direct chat person who's uh explaining about Monday. I hear you. Thank you. Understood. And it is 7. Okay, thank you. Sorry. Well, okay, I'm gonna screenshot it. I mean, I'm gonna screen share it in a moment. Just bear with me. But again, if you, well, yeah, bear with me for a second. But definitely, I mean, we ended at a conclusion Monday. We did end with an answer, which is good. I mean, so we did get to like where in principle I wanted to get, um, but feel free. Okay, hold on. I apologize. All right. Is there any, and there's nothing in the chat. Okay. And okay. So I'll screenshot. I'll screen share just for a moment so we know what we're talking about here. We are talking about this. Yes. All right. So, and this, as I recall, or because you pointed out, this is not due yet. I think this is due like Monday or it's due next week. It's long. But what this whole packet is about is the mathematical tool that we use to analyze situations, experiments, and problems in higher dimensions, in 2 or 3 or 4, etc. dimensions. The whole underlying, well, the principle underlying all of this is Galileo's principle, but specifically, the whole idea here is that every single two-dimensional problem or experiment is really two one-dimensional problems occurring simultaneously yet independently. Like that's the whole deal with all of this stuff. And then, but then the computational technique we use and the representation that we use to apply that principle to actual problem solving is we use vectors, right? This is all about vectors now. And a vector is an arrow that we use to represent a vector quantity, a quantity with magnitude and displacement, and our belief. So just like summarizing what we did yesterday, obviously, I guess. Our belief is that this, when I say that a vector is a representation, when I say that the size of the arrow represents the magnitude of a vector quantity and the orientation of the arrow represents the direction of the vector quantity, I want to make clear, or part of what yesterday was, Monday, was trying to make clear, is that it's not a loose representation. We don't mean representation like indication. We mean it's specifically point for point, like it's in one-to-one correspondence. The arrow is in one-to-one correspondence with the vector quantity. So a vector arrow is like a graph, or other tools of mathematics and science, or we trust that if we're drawing these arrows to scale, they actually can do accurate computations for us precisely. And honestly, that's really kind of the background idea of lab 3, is that if you draw stuff carefully with arrows and you take their orientation and their size seriously, then the arrows end up doing stuff for you, generating numbers for you that you don't actually need any other tools to generate. And that's true of any kind of vector quantity at all, whether it's displacement or velocity or acceleration or force or whatever, field. What we did Monday and what's going on through this entire sheet, this entire packet, what we did was we added two vectors together. And I want to emphasize, in fact, it doesn't say this yet on the sheet, but I want to emphasize that addition of vector quantities is a crucial skill. It's like going back to second grade. We're like learning how to add here, only we're learning how to add quantities that point in various directions in higher dimensional spaces. So we're learning how, like when you Monday, in principle, you learned how to add like 5 meters to the northeast plus 8 meters to the northwest or whatever, right? All we did was add, but we added two numbers that had directions associated with them and whose directions were not just as simple as like up or down, but we're at angles, right? We learned how to add. Whatever we did in order to add will work even for quantities. And this is a point of the packet that you'll see. That method of adding works even when it's harder to picture the quantities that we're adding or harder to picture what it would mean to add them. And the two things, again, this is just like to summarize or whatever. The two big takeaways from Monday is one, if you want to graphically, visually add two vector quantities, you place the arrows tip to tail, and the remaining arrow that would complete their triangle is the represents the addition of those two vectors. Again, that's lab 3. That if you place the tail of one vector on the tip of the other, you are representing their accumulated effect. And if you literally completed the triangle with a careful ruler and careful use of a ruler and careful use of a protractor, the measurement of that third side would be the answer in magnitude and direction. Like, that's how accurate and powerful these representation tools are. So that's the graphic method or the visual method of adding vectors, which is, but if you want to do it analytically, what we did, and this is now where I'm going to move on and start applying to this packet, what we saw is that analytically, the way to add two vectors is to break each vector apart into its perpendicular components, to ask each vector, what is your impact on the x-axis? What's your impact on the y-axis? And then run an accumulated, like run a table, make an XY table or an XY chart where we just accumulate up all the effects in the x-axis and independently accumulate all the effects in the y-axis. This method would work for as many vectors as you want. It doesn't have to just be two vectors. And frankly, it can work for as many dimensions as you want. The whole idea is that you break each vector down into independent yet simultaneous motions, and you treat them all independently, and then using your knowledge of right triangles of SOHCAHTOA and Pythagorean theorem, and then you put it all together at the end using your right triangle knowledge, SOHCAHTOA and Pythagorean theorems. Okay, so that's what we did on Monday. That's a summary. Now, all of this stuff in this huge packet is practice of various kinds. With that, only the packet transitions you from picturing displacement vectors to picturing the more abstract things like velocity vectors and ultimately acceleration vectors. Okay, that's the summary. Now, so looking at this sheet, it starts right. It's starting in 1D, so it's just trying to build up and show you the concept that I just explained. I'm making a quick decision. Yeah. I'm looking at the chat. I'm sorry, the chat. Probably the chat's been sitting there for a million years. I'm sorry. Hold on. Oh, wow. Oh, oh, oh. Oh my God. Okay. Huh. Amazing. And thank you for bringing it full circle. Okay, someone in the chat just had a conversation. But someone in the chat just asked what if you have more than two vectors? Okay, so I happened to answer it after they asked, but then they totally acknowledged that, which I totally appreciate. But yes, so let me explicate that for everybody. Yes, part of the power. See why let me say this again. We are learning how to add here. I mean, weirdly, like we're going back. We are learning this fundamental skill of adding. Now, of course, you all already know how to add numbers, but you also know how fundamental that is. Why did you have to learn how to add numbers in like second grade or whatever? Because the applications are beyond belief, right? Same thing here. We're learning how to add now vector quantities. And yes, the method that we're learning is super fundamental. Not only does it work for any type of vector quantity in physics, even some vector quantities that we've never heard of yet, but it's a method of addition. So absolutely, it works with as many vectors as you want. And and it works for as many vectors as you want in as many dimensions as you want. So we are, yes, we are. So good point that someone just pointed out in the chat. Like anything that we do here is extendable. That's like why it's a big deal. Um, okay. Um, I think I want to go. I'm going to ask you honestly. I feel like this first page of the sheet is literally a review of what we did yesterday. Um, I mean, the first part is even sort of more fundamental. It's just the first part is like a review of what we did like in the first week of class in a way. Um, oh, except for one thing. One second. Like basically, I'm going to skip unless you tell me in the chat, and you can, and I won't be insulted. But I'm largely not going to go over 1A and B here because I feel like largely they are what we've been doing. Um, except there's one thing I want to say about them. Well, no, yeah, I think, unless you tell me in the chat otherwise, I think 1A and B, if you look back at your notes, you should see that they are what we did yesterday. Um, right. But now, oh, chat, I'm looking at the chat. Okay, so maybe I should go over it. Hold on, hold on. Oh, we're good. Oh, good. Cool, cool, cool. Fine. That's awesome. But two people said we're good. I agree. That actually makes me really happy. I mean, that you're okay. So now I'm going to go to this then. And obviously, I'll switch the screens in a minute, but okay. The what? Oh, wait, there's more in the chat. Sorry. There's more. Oh, on part two. Oh, yeah. On part two, please. Yes, many new things there. Wow, you guys are wait. Oh, not this. Wait a minute. I was about to shed light on what is on the screen right now. Is that not what you're asking? Hold on, let me just see. Is that not what you're asking? Oh, you're saying part two. Oh, yeah. Okay. Same. Oh, okay. 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 Yeah. 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 Okay. I could do it either. It's the same point. Yeah. 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 Chat. One of us is not awake, and I think it's me. Yeah. Okay. 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 All right, I'm gonna back up for a second. It's all the same. Basically, and I'll oh my God. Basically, what I'm here to talk to all of you about, the thing that you need to see, I think that we need to see is how we move this concept of addition of vectors into velocity vectors. Like that's the key transition now. Okay. What we did Monday, and it is a thing. What we did Monday was we added vectors by two methods, graphic and component, right? But we used displacement vectors as our example. Now, let me slow this down and make this, and then had you practice that again in part one. But let's be very clear. I mean, let me try to be very clear. The thing with displacement, and that's just like what you did in lab three. The thing about displacement vectors is that anything that works for them works for all vectors, but they are necessarily the easiest ones to picture and believe in for all of us because the tool of the arrow that we're using to make a displacement vector, I mean, to represent a displacement vector quantity, the tool of the arrow, like it actually is the thing that we're representing. That, that is, say you're representing 3 miles to the east, then you draw an arrow on your piece of paper that's pointing to the east or whatever, and it may not be 3 miles long. It's probably 3 inches long or whatever, right? Like tacitly, you pick some scaling factor and then you stick with that scaling factor so that then when you have an arrow that's like supposed to be 6 miles, you make it 6 inches or whatever. So, but that's all it is. A displacement vector arrow is literally a displacement that's just been scaled down to the size of your page, which in fact is why they call the number three a scalar, because a display, in other words, you draw an arrow through space that takes up distance on the page, and that distance that it takes up represents an actual distance in real life, in real space. So the only thing that is representative about the arrow The only thing that isn't real is that the numbers have been shrunk down. But it literally looks like the exact thing that you're asked your brain to picture, which is distance in space, right? So that's a displacement vector. So when we were playing with arrows Monday, we were playing with the thing that we were actually thinking about. That's what makes them sort of concrete and comparatively easier for everybody, physicists, physics students, whatever. Now, I want to say that a velocity quantity is a vector quantity. It also has magnitude and direction. But okay, I'm going to start switching the page in a second. I will deal with this, but it's just my. But when you draw an arrow, well, okay, so I'm going to switch the screen. Well, I'll say this. When we now use arrows to represent velocity vector quantities, that takes a level of abstraction of the mind. Like that is slightly more challenging to all of us because when we draw an arrow on the page now to represent velocity, the length of the arrow represents the magnitude of the velocity quantity, i.e., the speed of some object. So the longer the arrow is on the page, the more we're supposed to be picturing that some object is going really fast, okay? But really fast in that moment. Like these velocity vectors that in fact, you may want to write this down. I mean, I will switch screens, but you may want to write this down. From here on in, when we talk about velocity vectors and we talk about adding velocity vectors or whatnot, we're tacitly talking about instantaneous velocity vectors. I mean, 99 point, I think 100% of the time in this class, and I think 99% of the time, like in life, we're adding or subtracting or manipulating instantaneous velocity vectors. So every arrow that's going to be on the page is going to be, when you look at it and you look at this really long arrow, you're supposed to be picturing an object that's moving really fast at some point in space and time. This point in space and time that's actually represented by the tail of the arrow, just the dot that the arrow like started from. You picture some boat or whatever, yeah, rowboat or whatever, or speedboat or whatever, or person. You picture them at that dot in space at that moment going super fast if the arrow is really long, or super slow if the arrow is really short. But okay, so I'm trying to drill here. Like already, the first thing to understand about velocity arrows is yes, all the math is going to work the same as displacement arrows, but length on the page does not tell you anything about how far some rowboat or some speedboat or some person goes. They're just telling you how, right? There's like no intervals being captured by these arrows on your page when you start drawing velocity arrows. What's being pictured is motions taking place in points of space and time. That's number one. I'm gonna okay, I'm gonna switch. Okay, so that's the first thing to understand. Wait, I'm just switching the screen so I can like start drawing stuff, whatever. Sorry. Um, Okay. Okay, so the comments I just put, oh, can you see? Wait, I'm sorry. Am I on? Yeah. So the comments I just put on the screen are just a summary of what I just said. So we're looking at now addition of velocity vectors. We're looking at part 2 of homework 7. In comments 1, just understand the addition of velocity vectors works the same way as the addition of displacement vectors or any vectors, right? So the goal here, the goal here is to see how we're just going to carry over the exact same drawing, like tip to tail method and component method of adding vectors is the rest of our life. We're gonna, and I mean that, like the rest of my life. It's all I do all day. Is either put vectors tip to tail or I break them apart into components and tally up their components. Like no matter what. That's comment A. But then comment B is understand now each next type of vector quantity we look at, the arrow that's on the page that's doing stuff for us is representing an increasingly abstract measurement in space, right? Like that's the thing to have in your mind, like right now. So now I'm going to continue with that point B to specifically what does it physically mean to add velocity vectors? This is the issue that I need to address. Like I could right now, like really, I could right now, or and this is why the homework is the homework and why it was assigned before. We could just give you two velocity vectors. Say this is velocity, like here's a velocity vector, like 10 miles an hour, 10 miles an hour to the northeast, and here's a different one, 20 miles an hour to the southwest. Add them. Okay. And you should be able to do it like by the exact same methods that we said Monday, right? But that would lead to two questions. One, what the heck did that mean in the physical world? And then you would get an answer, right? But number one, what would that answer mean in the physical world? That's a legitimate question. Like, how can you even picture it? What did you just do? And then number two, also, to be more realistic, since this is like physics and this is physics class, we probably ultimately don't just want to be able to do that. What if a person came in with a word problem? What if someone came in and described a situation with a bunch of velocities or whatever? How would you know which whether to do addition in the first place or which ones to add to which ones or whether you're supposed to be doing subtraction? Like what is the physical significance of putting velocity vectors together, right? That is a question that needs to be answered in order for us to even know how to set up these computations and make sense of them, i.e., like how to do step 3. Okay. So that's what I have to answer for you. That is what am I going to that is what part 2 page whatever page it is, the page part 2 relative velocity vectors is trying to get at in part through the back. It's trying to get you to see what these things mean, and then page 3 of the homework, when it all of a sudden looks super mathematical and intimidating, rule number 1, rule number 2, I'm totally going to explain. I promise my goal for today is really to explain all of that that's on the page that the person asked me for. But like usual in physics, we're trying to guide you toward that. Like we're trying to show you how it actually naturally will make sense and unfold for you if you read the page before it. Okay, so oh my God, sorry, my thing is freaking out. So what I'm going to do now is that I'm going to yeah, I'm going to switch screens again. Sorry to keep doing this. I don't want to hopefully it's less confused. So I'm going to go back. What I'm saying is this. What I'm saying is what I'm attempting to do right now, what the homework is attempting to do when it gets to this page right here, which I think you can do this page without my help. I think many of you. But why am I asking you to do it? Because this next page, it's hard to do without my help, or hard to like absorb without my help, right? But the idea is that this page like starts to make it make more sense for you. So I'm going to quickly say, if you look at this page right here, I'm sorry. If you look at this page right here, you're a rowboat on a choppy ocean. There's no land in sight. You have no radar. Blah, 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 blah. Is there any way to tell which way you're actually going and how fast? Why? How? No. Like this is train of thought, right? The point is, if your speed is not something that applies to a solitary object. The only way to talk about how fast you're going or in what direction is to compare to another object. That is the principle of relativity. That is GPR, like form number one, form number two, form number three. However you. So no, the answer is no. Right now, a speedboat appear. I mean, and by the way, that's like a huge. I mean, I'm going to go on, but you spend the rest of physics turning that idea over in your mind over and over and over, and eventually brings you to Einstein, and it brings you to twin paradoxes and black holes and everything. Like, so I'm not saying that's an easy idea, but you do want to let me know in the chat or in a text or an email if that idea seems unfamiliar to you, you want to let me know. Anyway, a speedboat appears on the eastern horizon. You see it coming to you at a speed of 40 meters per hour relative to you. Okay, so now there's a speedboat going 40 miles per hour relative to you. Okay, so it's going 40 uh, miles per hour to the west relative to you. The velocity of the speedboat is 40 miles per hour to the west relative to you. But now, if you were in, so now, if you're in the speedboat, part C, I hope it's clear to everybody. Now, here's where I want to slow this down because everything I'm about to say, the idea is you probably know it. You're probably not going to be surprised. You might even think it's a trick question. It's not. But I'm just setting up the English that we're then going to capture in symbolic equations on the next page. Okay, this is just trying to get you to see what is true. And then we're going to, but then what you might not have known was so important. So then we're going to capture it mathematically on the next page. Okay, so it says like, and this is the way physics always is, like every next step we really believe like, oh, if I had nothing else to do but just think about this, I would have come to that next step on my own. Like that's the theory of all of this, especially once you get practiced. So now imagine you're the person, so relative to the speedboat, the rowboat, I hope you all agree, is going 40 miles per hour to the east, right? It's like a mirror image, right? If I on Earth experience the sun going 65,000 miles an hour every day to the west, then if I were standing on the sun, I experience the Earth going 65,000 miles an hour every day to the east. And the key point, and I think you all believe that. I mean, I think you all understand that. The one thing that physics is telling you before we go any further is both are equally correct. That's not an optical illusion, and it's not just a fun game to play with yourself when you're 5 or you're stuck on the highway. Like that is reality, that there is more than one reality, so to speak, to velocity going on. And both are equally correct and both are equally useful depending on the circumstances. Like that's what we're trying to drill down. So then D, okay. By the way, one question that this should ask that it doesn't, let me slow down for a second. If I'm really trying to be clinical about this. So far, I'm trying to say that whatever you're doing to someone else is what they're doing to you in the opposite direction, velocity wise. Like, right? That's one thing I'm saying. Also, I should say to be clear, if if this had asked relative to you, how fast and in what direction are you going? Like if it had, or put another way, if it had asked relative to the speedboat, how fast and in what direction is the speedboat going? I almost want to pause and ask you to do that in the chat. If you hear me right now and you feel like it, just put it in the chat, direct or public, just so I know. Like, I'll just say it again. It's not a trick. I'm just trying to lay out things that actually are true, but actually matter more than you might realize, than I might realize. Like, how fast are you going relative to you, video gamers? I actually am going to pause to see if anybody, I'm going to say it one more time. Compared to you, how fast are you going? Should I say it one more time? This is off page, but oh, there we go, chat. Okay. And I'm not trying to trick you. I swear. Yes, awesome, awesome. I just got two direct chats and they're both correct. Yes, zero. Okay. You are, yeah, no, no, you don't sound dumb. No, it is zero. And this is okay, I'm getting, see, if I know it takes me so long to get warmed up, it's so crazy. The class should be 3 hours, shouldn't it? Because it takes me like 2 hours even to get somewhere. I'm just kidding, except for the last part. But I'm getting excited because I'm saying things that I know you understand because four of you just put in the chat, and one of you even thought it was like dumb even to put in the chat or for me to even ask, right? But I'm telling you all, the secret to physics is that everything in physics, in and of every little step of physics, is dumb. Not truly dumb, but every little step is accessible, and none of it we just make up and pull out of a hat. Every step in physics is the next natural thing that is almost so obvious that it doesn't even feel worth saying or thinking. It doesn't make you feel smart to say or think. But the smartness of physics, the brilliance of physics, is that it turns out that each one of these little steps actually does matter, that they mean something about the world. So for example, yes, all of you, right? It always feels like a trick question. I'm serious, and I will move on in a minute. But this page right here, that almost seems like a waste of time, is just trying to lay out the three different implications of the big fact that you could be on an Earth that's zipping through space at 65,000 miles an hour and not feel it. Like literally, physics is just a big box that opens up once we accept that package. And every little ingredient in it is these little sort of obvious things that the only thing that's not obvious about them is how much they matter. Okay. So the two things you're telling me so far in the right, no, and I'm down. Like it does seem like a trick question. It does, but it's not. Um, it- and sidebar, somehow I do know, I'm not kidding myself and I'm not trying to kid you. I know that physics adds up and eventually feels hard. I mean, even like in the middle of a homework, it feels hard. I'm not trying to say that it always feels easy. It always feels hard. But I am promising you this. There's something about physics that ends up being tricky enough. No, really, there's something about Mother Nature and the universe that is complex enough in the end. Physics is an attempt to make sense out of it. Physics is the attempt to simplify in our brains the complex universe that exists outside our brains. I'm serious. We're attempting to make it accessible to ourselves. So I promise you this, if you haven't gotten used to it already, the universe is tricky enough. So whenever I'm asking a question or putting something on an exam or this or that, 99% of the time, you should, well, really 100% of the time, you should assume that I'm not trying to trick you. If you ever have something in your mind that seems simple or a choice between two things, one is more simple interpretation and one is more complicated, you as a physics student and you as a physicist should always choose to assume the simpler interpretation. That is what we're actually doing in physics. Assume I'm not trying to trick you. Assume things are already tricky enough that I don't have to do that, right? To to we're trying to figure out the trick to all of us anyway. But really, like even on an exam, if you on a moment, if you're like, wait, he could mean this, but that seems too simple. It's got to be something. No, if you see something that you think I mean and you think it's it, yes, probably that is what I mean. But anyway, all right. So the two things that you've unlocked so far on this page are anything is going zero relative to itself, and anything that's going a certain velocity to something else, well, the something else is going the exact same velocity, but in the opposite direction. I mean, the exact same speed, but in the opposite direction. That's two truisms that we're saying here already that are going to turn into how we add velocity vectors if I ever get there, which I will, because we still thankfully have 35 minutes. So then the complicated part, I mean, the part, yeah, where it gets a little bit like, is part D. Now we have a speedboat passing a rowboat, but shooting a torpedo to the north. Okay, so now what? So now my head is like, the torpedo continues to travel to the north relative to the speedboat. In other words, if you're in the speedboat, you see the torpedo always staying due north of you, traveling due north, like a lot of words, but just to whatever. But if you're in the rowboat, what direction would a person in the rowboat see the torpedo moving? Okay, so it's not asking for any numbers. It's trying to get you to picture something that's already a little bit much to picture. And it's ultimately asking something about direction. Okay, and it is a lot, but it's trying to be as little of a lot as possible, i.e., a lot of those words, what they're really there to do is to answer the question that you would ask if the words weren't there, which is what this situation is trying to nail down is everybody, we're going to be just in one dimension for a moment. We're going to look at just one dimension. We're going to look at everything just going north, but we're all going to calm down and think about it calmly for a second because the new complexity in this part D is that now for the first time we're talking about three objects. That is why the head is maybe a little bit like adjusting itself. There's three objects now: a speedboat, a rowboat, and a torpedo, right? And we got a speedboat. We got a speedboat passing a rowboat, and then a torpedo coming out of that speedboat. But everything is north. So what I think you know is that the answer to this question is north, right? I mean, unless like you got a speedboat going. I'm just checking. Is the speedboat? Wait, oh. Oh, no. Oh, it's sorry. Actually, wait. I mean, yes. I mean, everything I said is right, except for one thing. Are we still in one dimensions? We may actually be in two dimensions. Hold on. The person in the rowboat. Oh no, we're in two dimensions. I'm sorry. So we've got um a a speedboat going west compared to a rowboat, and then it shoots a torpedo to the north compared to that speedboat, right? So maybe I should just pause and ask you. So the question is, what's the torpedo doing relative to the rowboat? And yes, two dimensions are involved now. My bad. Two dimensions are involved, but no numbers or anything like that. Just two dimensions. So and I guess I have time to ask you if, and you may want to draw for yourself or in the homework. But we got this boat going like that, and then out of the boat comes a torpedo going like that. So the question is to the rowboat, what does it see? What does it observe the torpedo doing? And I'm asking, like, in other words, is it north? Is it east? Is it west? Is it south? Is it northeast? Is it southwest? Is it what is? So I'm asking you to put in the direct chat, just a word of English. What is the torpedo doing relative to the rowboat? What direction is it? So please, and I'll wait till there's at least three things in the direct chat. I'll repeat. So the question is D. I'm asking you to do right now, even if you haven't done the homework yet, like just think about it right now. If you've got a you've got a speedboat that's going west compared to a rowboat, and then it shoots a torpedo that's going north compared to the speedboat. So what is the torpedo doing compared to or relative to the rowboat? That is the question I would like you to put in the direct chat. And again, what we're looking for is an answer such as north or south or southeast or southwest or north. Like that's the kind of answer. Okay, that's one person in the chat also. And direct chat, please. I mean, I think that was. When I get three, I'll move on. But I just want to see. Awesome. That's one answer. That's two answers in the direct chat. Awesome. And I'm even going to say, there's two answers in the direct chat. When I get one more, awesome. Awesome. Okay. And you can keep them coming, but I'm satisfied. So there's three answers in the direct chat, four answers in the direct chat. Awesome. I love this class. I'm not kidding. Do I ever not love a class? Yes, I actually do. It doesn't happen often, but it does happen. And this is not one of those times. Five things in the direct chat. Okay. And I'm going to stop because not only are there five answers in the direct chat, every single one of them is identical and every single one of the answers is correct. And they all say northwest, which I'm very pleased. Thank you. Yes. Oh, yay. Okay. Awesome. And you should all submit for points, including the oh, yay. It's like self multiplayer co-op or something. So northwest. Now look, you notice that you all got that. I don't know if you did it at home or you did it right here, but like you didn't have to like kill yourself to do it, right? But what you just showed, you just took matters to a context of three objects in two dimensions. And what you just showed is, at least before we start crunching numbers, you showed conceptually that you do know what it means to add velocity vectors, well, to add velocity vectors even in two dimensions. What you just showed is that you understand the three object case of velocity addition. What you just showed, now I'm going to say this a couple of different ways. I'm about to graduate to the next page with all the symbols on it, okay? But and this is what I'm about to say also is literally what I wrote on the front page of the notes of PDF today. I mean, you know what I'm saying? Like, if Galileo's principle is really true, then that velocity is a relation, not a property, a relation between two objects, not a property of one. Then what that really means is, from now on, when we write velocity, and when we're being careful, we don't just write v. First of all, we'll often write an arrow over the v to indicate that we mean velocity as a vector quantity. Like, we'll put arrows from now on whenever we're talking about vector quantities to really make explicit that we have to track magnitudes and directions, and to make explicit that direction often from now on might involve angles and points of the compass, right? So from now on, when we write v, we write it with an arrow over it. But more to the point, we often will follow the v with two subscripts, like AA or AB or AC or something. And the two subscripts are there to remind us that velocity is a comparison between two objects. And from now on, if you picture the letter A to represent some object, A, moving at some speed in some direction, and B, lowercase b, represents some other object moving in some speed in some direction, and C, etc. If every little lowercase letter represents some other object, then what you're telling me is that the Galileo's principle can be understood in three cases: the case of one object, the case of two objects, and the case of three objects. The case of one object, well, here, okay. Well, here it is on the next page, right? This thing. Oh, and everything I'm about. So I'm going down to rule number one, rule number two, rule number three, like on the next page. And what we're really trying to argue is we always knew this was true about displacements. And in the back of our mind, we even kind of knew it was true about velocities. We just didn't really know that we knew it or know that it was important. So I'm skipping right to the velocity part. I'm saying that Galileo's principle of relativity can be understood to be form number 5. We're up to form number 5 now. I'll switch back to the board. And form number 5 is three cases. The one object case, if you just have, I usually use lowercase letters. This sheet is using capitals, but it doesn't matter. And A, B, and C just mean three arbitrary objects. They aren't like they could be D, E, and F. They're just arbitrary objects. But we're saying from now on, if you just have one object in the context, then the velocity of that object to itself, relative to itself, is 0. The velocity of it, but if you have two objects, rule number 2, the velocity of one object relative to a second one is the opposite of the velocity of the second one relative to it. Again, you already knew that, like back on but now we're saying, no, this is actually important. And before I go to the third one, which is the big one, that's the big one, notice order like matters. And you may want to put this in your notes. I know I'm all over the place here, but if I write VAB, I literally mean velocity of A relative to B. I really would suggest you put this in your notes because I'm like on 3 screens at once here. But if we write V subscript A subscript B, we mean the velocity of A relative to B, which means the velocity measurement for A as measured by B, or put another way, we mean the velocity measurement for A that B would get, assuming that B regards itself as stationary. I'm going to put it one other way, then I'll repeat that. VAB, put another way, means the velocity of A in the frame of reference or in the reference frame of B. Like all those are equivalent, what I just said. But you notice the order does matter. Otherwise, in rule number 2, when we switch the order, we get a negative sign, right? Like order matters. But VAB means velocity of A relative to B, velocity of A compared to B, same thing. Velocity measurement for A as measured by B, velocity of A assuming B is stationary, like has a velocity of 0, velocity of A in the reference frame of B. All of those are different ways of saying the exact same thing. And if anybody wants me to repeat any of them, yep, there we go. Chad, hold on. Fair enough. Yeah. So the negative sign in rule number 2, right, means literally same magnitude, same speed, but in opposite direction. Yes, that's what the negative sign means. And let me be even more clear, or try to be more clear. If we're now in 2 dimensions or higher dimensions, then a negative sign literally means flip the vector. Flip the whole vector, right? So if the velocity of one object, if VAB is like 30 miles per hour at 40 degrees northeast, then VBA would be 40 miles per hour at 40 degrees southwest. And tell me, person who just put that question in, like, tell me if that, like, right? You literally, the negative sign means opposite of the entire vector. So if the vector is going off on some diagonal line, you flip the whole thing. So you turn south into north and you turn west into east or whatever. So yes, negative literally means keep the same magnitude, flip the direction. The chat. Yeah, that makes sense. But now if you have to edit. Yeah. Oh, okay. Woo. So someone just, so direct chat person number 17. Wouldn't that be weird if I gave you, or whatever. The same direct chat person just said, yeah, that makes sense. But so now if you, oh my God. Okay. Yeah, I guess. But if you now have to add the vectors, the person says, okay, that makes sense, fine. But now if you have to add the vectors, do you literally put a negative sign during calculations though? Oh my God, what a great question. Let me repeat, because yes, I mean, I'm giving you the whole concept here. And of course, what we eventually have to see is like, how does this get put into practice with the numbers? And of course, that's my next goal. And of course, that's what you want to see. But just in case the clock runs out today, yes, let me say, I mean, that person's asking like, wait, when you're actually doing this stuff, if you're actually like adding, which is the point of all this, are you saying that you would like literally put negative signs in? So yes, I'm saying yes. I'm saying it's a great question and I'm saying it's yes, but I'm also, to be even more clear in case the clock runs out, which it totally will, I'm saying that once you know from what we're yammering about here is really how to know which vectors to add to which vectors, like when you get a velocity problem, like which vectors are being added to what to mean what. Once you know I'm adding the rowboat to the speedboat or whatever, which is what I'm about to explain, but once you know, okay, I'm adding this rowboat vector to this speedboat vector, then you're going to break them into components the same way you broke things into components on Monday, the same way you break up displacement vectors. You're going to break the velocity vectors into components, and you're going to make an XY chart just like Monday. You're going to do the horizontal components of all your velocities, like the X components, and you're going to do all the Y components of all your velocities. And in the chart where you're adding up the numbers there, and I believe we did this Monday. Yeah, we totally did. In the chart is where the negative signs will go. So if you get a velocity vector, if a velocity vector is going northeast, then the north piece of it like will be positive, and the east component of it will be positive. But then if the next vector is going southwest, if it's going southwest, then there'll be a negative sign in each of the numbers in the chart. If it's going northwest, then the y-axis would be positive, the y component would be positive, and the x component would be negative, like that. So it's a really good question. And I will show you, but in case I don't end up showing you today, negative signs still matter in our life big time. But what they're doing what they ever did before, which is making a distinction between two directions on any one given axis at a time. Once you're in a axis, that's when the negative signs get applied. And then you put together all the axes at the end with Pythagorean theorem, and you get one big vector that won't have a negative sign, like that will have angles and will have an angle. I hope that makes some sense. But we'll see in a second or in a day. Great question. What I'm getting at now is rule number 3. Rule number 3, okay, is what to do when you have 3 objects, and it's what you already believe in your mind, but it is a deep observation. Rule number 3 is what it's telling us. It's telling us what the actual meaning of adding velocities like is. This is what I mean. If I just throw something across the room, if I throw a baseball across the room, it's going 50 miles an hour, and then you throw like an orange across the room and it's going 40 miles an hour in a different direction. Okay, then my baseball is doing something relative to the room, and your orange is doing something relative to the room. Or I mean, we can measure those things, right? We could add those numbers together. Like we could take the 50 of my baseball and the 40 describing your orange, and we could add those numbers together. We could even add them together properly by component method, but it wouldn't mean anything. It literally would not mean anything. Like baseball to room plus orange to room equals number that nobody cares about. It has no physical significance. But what this thing is putting in symbolic form, it's capturing what you already understood in your mind when you added north and west and came up with northwest, which is that you can add velocity vectors meaningfully as long as you really take into account their relational quality, as long as you switch perspectives properly, then and only then you can add velocities. In other words, what rule now this is deep, okay? And this is where people get this is what I wouldn't have thought of on my own as such without physics and like what takes a while to practice. I'm saying rule 3, or what I call this sheet is calling rule 3. I call it case 3 of Galileo's principle of relativity, form number 5. And I'll show you back on the board. It's the first page of the board, of today's board. It says VAB plus VBC equals VAC. Now that sounds like transitive. I mean, it sounds rhythmic and everything, and it looks, but what does it say? So it's like not hard to memorize if that's your goal, but like, what is it saying? It's saying we add velocities when we have more than 2 objects. When we have 3 objects is when we add velocities, and we add them as long as we have at least in order to add them, we need 2 different perspectives to add from. What it's saying is the velocity of the torpedo, like pretend object A is the torpedo, object B is the speedboat, object C is the rowboat. It's saying velocity of the torpedo relative to the speedboat plus the velocity of the speedboat relative to the rowboat gives you the velocity of the torpedo relative to the rowboat. That's what it's saying, and that's what you sort of already knew, at least in a simple enough case, but it's saying it's true in all cases, even when they're really complicated, even when there's even when the numbers have to be crunched, even when none of the numbers is 0, blah, blah, blah. In other words, you know this. You know, I know, you know, velocity of U relative to the subway plus velocity of subway relative to New York City streets yields velocity of U relative to New York City streets. And that's why you take subways, because you can chill on a subway, right? You can get on a subway and be like, and sit down. And what does it mean, sit down? It means the velocity of U relative to the subway is 0. You're not doing anything. You're taking a rest. But the velocity of the subway is 80 miles an hour relative to New York City streets. Therefore, the velocity of U is now 80 miles an hour relative to city streets. So you get where you're going without doing anything, right? Well, so of course everybody knows this. That's why but what we're saying is, yeah, but guess what? that easy to picture case that had zeros involved and all had one dimension, that's true no matter what. And it doesn't matter whether it has nothing to do with engines. It has to do with the nature of motion. Like, well, like even when negative signs are involved, if you start walking backwards on the subway, you're like, if the subway's going 80 miles an hour relative to the streets, but or try it on an escalator in Columbus Circle, as my sons used to do when they were little. Like if the escalator is going 5 miles an hour up, but you walk, so it's going 5 miles an hour relative to the mall, and you're walking down relative to it at 2 miles an hour, right? Then you're only going up relative to the mall at three, like right. And what we're saying here is this even applies to two dimensions. So when you get, even though I know I'm sort of running out of time, when you finally, so this page was just trying to show you that you already know this, that what it means to add velocity vectors, we're going to mathematically add them by the exact same method as Monday. Break them into components, make an XY chart, add up, tally up the components individually, and then put everything back together with Pythagorean theorem and sorry. We're going to do the same math as Monday. You're going to do the same math. Like when you get like to this sheet. But what this sheet is trying to tell you, sorry. Well, what this sheet is trying to tell you is the way to know which velocities get added to which is velocity of A, velocity of object number one relative to object number two, plus velocity of object two relative to object three yields the velocity of one relative to three. And all of those three velocities are equally correct. It's not like any one is more truth than any other. It's just a way of looking at the world. Okay, that's what it's trying to tell you. Yeah, in that sheet. Wait, I'm looking at the time. So then like it's practicing that here on this sheet, but in this sheet, again, now that I've said all that, hopefully this sheet would be easier. But honestly, you would probably get a lot of this sheet right, even without all of what I said, because you're picturing it in one dimension. And I think people understand this when it's in one dimension. But by the time you get here, in the homework, the you literally have to take what I just said, VAB plus VBC equals VAC, or you could say it the other way, VAC equals VAB plus VBC. You take that as your step 3 GDP. And then when you're starting to, then when you say, okay, I've got to add this velocity vector to that velocity vector, then in order to do it, you break things into components using SOHCAHTOA, just like we did Monday. So it's Galileo's principle of relativity being applied to the concept of vector addition. That's how we add velocity vectors. That's what all of this is trying to say. I'm just looking at the time. I mean, obviously, I would like to do a concrete. Oh, yes, thank you. Yes, Colin, please. Yes, Colin.
For the extra credit problem with the torpedo,
Oh,
uh, do we need to know the velocity of the torpedo to know the angle, to calculate the angle?
that is a really good question. Wait, I'm looking. You're talking about right here. Okay, wait, good question. Um, that is a good. Yeah, I would think you would. Hold on, let me just look at it carefully to see if this is a. Um, yes, you would. Why does it? Yeah, I agree with you. Wait, 40 is. I'm just looking if it's like secretly given somewhere. Yeah. You're absolutely right. So let's say that right now for anybody who wants to do this. I don't know why that's missing. You could tell uh, the sheet is partly made by a very trusted old colleague of mine whom I love, but I didn't. Yeah, but anyway, yes. So for E, if you want to do the extra credit, let's say, can I write it on the thing? Let's say that the torpedo is going 10 miles per hour, 10 miles per hour relative to the speedboat. I'll write it on the, that's a great question and totally submit for points for that observation. Let me just see what's the fastest way I can do this on the, uh, I'll just put in the chat, I think is, oh no, okay. Oh yeah, okay. Okay. No, and that's a great actually note to end on. I mean, look, I promise that next class I will do out a computation for you guys. That presumably that would have been ideal, I guess, today. But the I'm saying again that the computation technique is literally what we did Monday. Now everything what I'm adding today is how you know what to compute with what and what it means. But then even notice, I mean, Colin's question is a perfect note to end on because yes, like this extra credit here would be a great, I mean, it's extra credit, you don't have to do it, but it's on the other hand, it's a perfect warm up to the rest of the pages. If you can follow even why Colin asked that question, you're already in good shape. And if you can follow why I added the information I did the way I did, like I'm saying, I mean, it's hard for me to do subscripts, in the middle of the Zoom, but I'm saying assume VTS, meaning the velocity of the torpedo relative to the speedboat. I'm providing this number of 10 miles per hour. And to make it a velocity, I'd have to give you a direction as well. But the problem did do that. It says that the torpedo is going due north relative to the speedboat. So we've got a torpedo is going 10 miles an hour due north relative to a speedboat. We've got a speedboat going 40 miles an hour due west relative to a rowboat. So if you want to know what the torpedo is doing relative to the rowboat, you literally add those two velocities that I just said, 40 miles per hour to the due west and plus 10 miles an hour to the due north. You would add those together and get your answer for E, for what the torpedo is doing relative to the rowboat. And if you do them, you'll literally get not just the angle and direction, but you'll actually, since Colin just gave, like, since we just gave you a number, you'll get a speed too for your final answer. And I'll say this now, we're going to actually end there. Hopefully that makes some sense. Like, that's a good practice problem for the rest of it. You will get a number. Like if you add VSR plus, sorry. Well, yes, if you add VTS plus VSR, you might want to write this down, you'll get VTR. Where did I get TS and R? Well, I'm saying, remember, A, B, and C are just any three arbitrary objects. So my three objects are torpedo, speedboat, and rowboat. So I'm substituting in T, S, and R, like T for torpedo, S for speedboat, R for rowboat, right? I mean, the point of that thing that's written on the other page is the pattern of the letters, right? There's nothing magic about the letters A, B, and C. So the principle here is torpedo to speedboat plus speedboat to rowboat equals torpedo to rowboat. You can make other combinations too, but that's the combination that it's asking for here. Um, um, so if you do this, if you add, I don't mean add the numbers, like the answer, like how fast is the torpedo going relative to the rowboat? I know it's not asking that, but I'm saying if I were to ask how fast is the torpedo going relative to the rowboat, you know that you're beginning to understand what I'm saying, or you're like on the path with me. You'll know you are on the path with me if you understand that the answer is not 50. The torpedo is not going 50 relative to the rowboat. When I say add these velocities, I don't mean add the speeds. I mean add the velocities. I don't just mean add 10 to, like, that's not what you would see. You would not see a torpedo going 50 because it's the boat, it's going 10 out of a boat that's going 40, but the 40 is in one direction and the 10 is in another direction. They don't just add like number. You see what I'm saying? But if you drew out and you took components and you made a chart, you would see that the torpedo is probably going like 42 or something miles per hour relative to the rowboat. And it's not going perfectly northeast. It's not going to be 45 degrees. It's going more northwest. It's going more westish than it's going north. How do I know? Because it's going faster in the westish direction than it is in the north, right? So you're going to get something like 42 miles per hour at an angle of, like, I don't know, 25, like 20 degrees or something. I'm just, but like something lower than 45. You're going to get something like 20 degrees northwest. If you understand roughly what I'm saying right now, like what, then you get the concept. But how you would add the 40 and the 10 is you would literally, like Monday, you would break the 40 into a 40 cosine and a 40 sine, and what would it would be 40 cosine, it'd be 40 cosine 0 and 40 sine 0. It would. So one of the components will be 40 and one will be 0. That is true. That's not a problem. And then the other arrow would be like 10 cosine 0, or excuse me, like 10 cosine 90 and 10 sine 90. So one of your components will be 10 and one will be 0. And you think it's all going to like fall apart, but it's not, because then you make a chart and it'll, in the chart, it'll be like 40 plus 0 and it'll be like 0 plus 10 or whatever. So you get 40 and 10, and then you'll make a big triangle with the 40 and 10 and get the hypotenuse of that triangle. And the hypotenuse will be like 42 or something. I'm just yelling. But if you kind of, if you can 60% follow what I'm saying right now, then you get the point of today. I think Colin's question was great. Way to end. It's 12:04. Thank you for so much patience, and I will see you Monday. Bye. Yes, bye. Okay, and I'm stopping the recording. Okay. Thank you, guys.
Hey, Professor.
Yes.
I've,
Oh,
oh,
yes.
I've